So this is the second part of this lecture 0 for our CFD course, our review of the differential form of the fluid equations, and this second part will refer to the conservation of momentum, and we start with the equation for conservation of momentum for a system. For a system, we apply Newton's law to write the conservation of momentum as the following equation. It is the force equal to the change in momentum, the momentum being the integral in the system of the velocity times the mass, velocity times an element of mass integrated over all the system. For a control volume, as before, one can use the Reynolds transport theorem to write the conservation of momentum in integral form. And so for a control volume, we can write the sum of forces for the control volume is equal to, first, the unsteady term, partial derivative with respect to time of the integral in the control volume of the momentum, which is velocity times rho dV, which is our element of mass. And the flux terms. The flux terms are integral across the control surfaces of the flux of momentum, which is velocity times rho times velocity dot product with the outward normal and multiplied by an element of area. This is our flux of momentum. Now we apply first the system equation to an infinitesimal fluid mass. So consider now an infinitesimal fluid mass dm. Of course, for that fluid mass, we would have a df, a small force, is equal again to the change of momentum, d dt, of the velocity times the element of mass, which is equal to the element of mass times d dt of the velocity, which of course, as expected, is the acceleration. So df is equal to dm times the acceleration. This expresses Newton's law applied to the mass dm, as expected. Now, there are two types of forces that can be considered in fluids. So the types of forces. We can have body forces, and basically in this we consider the weight of the element, and it will be simply a differential of force, body force, equal to the mass times the acceleration of gravity. And we also have surface forces. We can have two types of surface forces, normal and tangential to the element of area. We will consider normal and tangential surface forces. So imagine that we have a piece of area in the fluid somewhere, and we consider an element of area here, dA, and in this element, let's draw our components of the surface forces. One will be a force normal to the area. Let's draw it this way, and this will be dFn, our normal, and then we'll have two components which are tangent to the surface but perpendicular to each other. Let's call these dF1 and dF2 to represent the two forces parallel to the area and orthogonal to each other. So delta Fn is the force normal to the area, and dF1 and dF2 are tangent to dA. So now we're going to be interested in the stresses. The normal stress is equal to, what we call it sigma normal, is equal to the limit when the area tends to 0 of dF normal divided by d area. And we have two shearing stresses. Associated to the two tangential directions, we call these tau. So tau 1 is going to be equal to the limit when the area tends to 0 of dF1 divided by dA, and tau 2 is the limit when the area tends to 0 of dF2 divided by dA. Now, normally we will want to write these stresses with reference to a coordinate system. So to write this with reference to a coordinate system, let's imagine a box here. Let's write our coordinate system, which will be x in this direction, y upwards, and z. And let's draw a box which represents an element of fluid, a cubic volume which has faces orthogonal to each reference coordinate. And let's consider the plane parallel to the xy plane. So the face parallel to the xy plane, here we're going to draw an outward normal representing our normal stress, and we call this sigma xx. We have one tangential stress here vertically upwards, and we're going to call this tau xy, and we're going to have another tangential stress here in this direction, which we call tau xz. So our notation is the following for the plane parallel to YZ plane. Sigma xx is our normal stress, and tau xy and tau xz are our shearing stresses. So the notation, the subscript notation is the first subscript represents the direction of the normal vector, and the second subscript refers to the direction of the stress vector. So you see, we have drawn here sigma xx, tau xy, and tau xz, and all have their first subscript x because they are stresses on this face, which has a normal vector in the x direction. And the second subscript indicates the direction of the stress vector, so the normal stress will always have two equal subscripts, in this case sigma xx, and the shearing stresses will always have two different subscripts. So this is our notation. We also need a sign convention, And we use the following sign convention. We define the positive direction for the stress as the positive coordinate direction on the surface for which the outward normal is in the positive coordinate direction. Now, I'm going to draw in the next page a little sketch about this to explain it. So we continue, and we are looking at the sign convention for stresses. And we said we define the positive direction for the stress as the positive coordinate direction on the surface for which the outward normal is in the positive coordinate direction. So let's do a plot to understand this. Again, we have a coordinate direction x, y, z. And so imagine that we are looking at a piece of fluid, and I'm going to draw just a piece of the cube here. Imagine a piece of cube, and I'm looking at this face here that is behind the cube. And here I'm going to draw the normal stress to this face, the normal stress, and this is going to be sigma xx, and the tangential stress in the z direction is this one, while the tangential stress in the y direction is this one. So we have here all stresses shown are considered positive because the outward normal points in the negative coordinate direction, and so the stresses are considered positive if they point in the negative coordinate direction, in the direction of the outward normal. On the other hand, if we're looking at this face of an element of fluid, then the outward normal points in the positive coordinate direction, and this would be a positive normal stress. This would be a positive tau xy, and this would be a positive tau xz. So this is tau xz, and this is tau xy. Here, notice that tau xy points in the negative coordinate direction, and it's considered positive because the outward normal points in the negative coordinate direction. On the right hand side sketch, we have the tau xy pointed in the positive coordinate, in the positive y direction, considered positive because the normal to this face is in the same direction as the x direction, positive. This is a little bit confusing, so think about it a little bit, look at these drawings, and I hope that you will agree with this sign convention. So now we look at the surface forces in terms of the stresses. And we're going to consider first all the stresses which apply in the x direction. So we consider a space varying stress acting on a small cube. Let's consider, we have our first same coordinate system as I've drawn before, and let's consider a small cube. So let me draw a small cube of fluid, and let's consider the normal stresses that apply on the x direction. So we'll have a normal sigma xx applying here, and a normal sigma xx applying in the back of this sketch of a cube. And we look at the variation of the sigma xx. We consider sigma xx to apply at the center of the cube, and therefore the variation of sigma xx with respect to x applying Taylor series is going to be, we have here sigma xx minus d dx of sigma xx multiplied by delta x half, which is the distance between the center and that face, and all of this multiplied, I didn't leave space here, multiplied by dy dz, which is the area. On the right hand side we have sigma xx plus now d dx of sigma xx, again multiplied by the distance between the center and this face, which is delta x half, and all of this multiplied by the element of area, dy dz, is going to be the force on the right hand side, pointing in the x direction. So those are the normal stresses. So let's consider now the stresses on the walls in the front and the back. So this is going to be this, I'm going to draw again our cube, and we have in the front a stress, and we're going to have also I've drawn it a little bigger so I can show in the back there's also another stress there in the x direction. So the stress in the front face is going to be, this one here is going to be tau z x z, because the outward normal on this face is in the z direction. The first index indicates the normal direction, plus d dz of tau zx multiplied by dz half and multiplied by the element of area, which in this case is delta x, delta y. The one in the back is going to be tau zx, notice I've drawn it in the positive direction, minus the variation, which is d dz tau zx, and the distance between the center and that face, which is dz half, and all multiplied by the element of area, which is dx and dy. So there I've drawn the two contributions to the force in the x direction due to the surface stresses, tangential on the front face and the back face of that cube. So now we need to consider the bottom face and the top face of the cube. So let me draw again a cube, and we'll have a top face, this one, and we'll have a bottom face underneath here, this one. So on the top face we'll have this stress in the positive x direction, which is going to be tau yz plus the variation d dy now of tau yz times the distance between the center and that face, which is dy half. Oops, the parenthesis goes outside. And times the element of area, which is dx dz. The one in the bottom face, underneath here, is going to be tau yz minus d dy tau yz multiplied by dy half multiplied by dx and dz. And I've noticed that I've made a mistake here. This is tau in the normal is in the y direction, but the actual stress is in the x direction. So let me correct that for an x. This is correct y, and this is supposed to be an x. And again here, yx. So you see, you have to be careful. It is easy to make a mistake. You have to be careful here with this convention until you get used to it. And so the stress itself points in the x direction. So sorry about that mistake. But now we have all stresses shown on the positive direction. And we have considered all the contributions to the force in the x coordinate direction. So we have the three possible contributions. So now we can write the sum of forces in the x direction. The sum of forces in the x direction due to the surface forces is, let's write it, df s for surface and x because it's the x direction, and that's going to be equal to, well, we sum all of these components and you see that because some of them are pointing towards the right and some of them are pointing towards the left, then the signs will turn out to cancel out all the terms sigma xx, tau yz, and tau zx, and we're going to be left only with the variation terms, which are ddx of sigma xx. The 1/2s also go away. ddy tau yx and plus dz tau zx. So all of the stresses point in the x direction, and therefore the second subscript, it has to be an x, and multiplied by the volume dx, dy, dz. Similarly, we can do in the other directions. So we get the surface force in the y direction is going to be equal to ddx of tau xy plus dy of sigma yy, the normal in the y direction, the normal stress in the y direction, plus dz tau zy, and multiply it again by the volume dx, dy, dz. And df surface in the z direction is equal to ddx of tau xz plus ddy of tau yz plus dz sigma zz. So you see the pattern there that results. Multiplied by the volume dx, dy, dz. So now we can write the resultant force. The resultant force, of course, is going to be the sum of the resultant surface force is going to be the sum of dfsx plus dfsy plus dfsz. We've written here the three terms with the respective normal unit vectors. So now we can see that we can write the equations of motion. We can finally write the equations of motion, and this is just a physical argument based on Newton's law rather than a mathematical derivation. Remember that we had that df is equal to dm times a. So we can do that in each direction, taking into account surface and body forces, the weight, with the, of course, dm is equal to rho times the volume, dx, dy, dz. And so we get, in the x direction, we have the weight, which is rho g in the x direction. We don't assume that g applies in any direction yet. We're going to divide over by dx, dy, dz everywhere, so I'm not going to write it down because it appears in every term and we can divide over, plus the surface forces in the x direction. We have dx of sigma xx plus dy of tau yx plus d dz of tau zx, and here are all our forces, and that is going to be equal to the acceleration. The acceleration is the unsteady acceleration plus the convective acceleration, which is rho times, in this case, in the x direction, our velocity is u, so du dt, the unsteady term, plus the convective acceleration in the x direction, so u du dx plus v du dy plus w du dz, our convective acceleration in the x direction. So now we can write the equation of motion in the y direction. We have our body force G y, rho Gy, plus ddx tau x y plus ddy sigma y y plus ddz tau z y equal to our acceleration on the y direction, which is rho times the unsteady term dv dt plus u dv dx plus v dv dy plus w dv dz. And finally, in the z direction, we have rho g z, if there was any acceleration in that direction, depends on our coordinate system, choice of coordinate system. That's our body force, the weight, plus ddx of tau xz plus ddy of tau yz and plus dz of sigma zz equal to our acceleration in the z direction, rho times d dt of w, the velocity in the z direction, plus the convective term u dw dx plus v dw dy and plus w dw dz. So here we have our convective acceleration on the right hand side. These are the equations of motions that represent conservation of momentum in the three coordinate directions. So there are three equations. And notice that the with continuity we have in total 4 equations, but the unknowns are, let's see, our unknowns are the 3 components of velocity, u, v, w, and all the stresses. So obviously we need more information. We will need more information. We will need some assumptions about the stresses. For example, we could assume, we're going to need to assume, for example, if we can consider inviscid flow, there will be no shearing stresses. We consider some constitutive relation and so on. But these are the general equations of motion using just physical arguments to derive them. An example of a simplification is the case of inviscid flow. For inviscid flow, we would have no shearing stresses. Because there is no viscosity, shearing stresses develop due to viscosity. So if we can neglect viscosity, there are no shearing stresses. And therefore, if there are no shearing stresses, the normal stress at any point is independent of direction. It can be proved I won't do it here, but it can be proved that sigma xx is equal to sigma yy is equal to sigma zz and is equal to minus the pressure. So that gives us Euler's equation. For example, in the x direction, we would write rho gx minus, so the term here that involves sigma xx turns into, instead of ddx sigma xx, we have minus ddx p dpdx, because we have substituted the normal stresses by the pressure. And on the right-hand side, again, we have the acceleration term, so we have the same as above for the first equation. In the x direction is rho du dt plus u du dx plus v du dy plus w du dz. So you can see we can write the three equations, the three component equations in the same form, but in vector notation, the three equations can be collapsed together. In vector notation, we can write then Euler's equations as rho times the vector g, acceleration of gravity, minus, we're going to have, in each equation, we're going to have ddx of p, ddy of p, and and ddz of p. So we have basically the gradient of pressure, and that is going to be equal to rho and times d dt, the unsteady terms of the whole velocity, plus the convective acceleration term, velocity dot product with the gradient, the divergence operator, and multiplied by the velocity again. So this is our Euler equation. Sorry, yeah, that's correct. Euler equation in vector notation. For the case of inviscid flow, again. For viscous flow, we're going to have to make some assumptions about the stresses. And that next step is going to give us the Navier-Stokes equations.